Hello, my name is Patrick Ajura. Today I'm going to briefly run through some basic mechanics to derive some laws for waves and simple harmonics and interesting things like that. So yes, my name is Patrick Ajura. You can visit my website by Google searching TIOKRS, or there might be a link underneath this for to view more material of this in greater depth. I'll be coming out with a book in early 2013 called Topics in Applied Mathematics, which will take this in greater depth. So, what are the laws? So, we know our general Newtonian laws of mechanics, and we want to use that to derive the equations for waves, how things oscillate. So, we'll begin by stating that F is equal to, F is equal to ma, which is m times the rate of change of velocity over time. So that's that done. We know that law, F is equal to ma. And so now do we integrate? Yes, we want to integrate. Yes, of course we want to integrate. We want to integrate. So the force, the total force applied over time is equal to the integral, so mass and the integral du. Now it's obvious how we got that. We have the du there, our dt goes there, and just integrate both sides. Nothing too difficult. This equation, this is known as the impulse. The impulse, that's what this is called, impulse. So the force over time. So the total force applied to a body over time. This is called the impulse. That gives you a value of, I hope you know this. This is merely the change in momentum. M times u2 minus m times u1. That means our change in momentum. Our momentum at the end of our analysis minus the original momentum. So m times our velocity at the end of time that we're investigating minus original m times our original velocity. M is obviously the mass of the body in question, and u is obviously its velocity. So we shall now go further to state that if we're travelling a long path with a function of x, the summation of our forces along this path x is equal to the work we do. So imagine you're climbing a difficult hill, Mount Hermon or Mount Everest. At each point, obviously where it's steeper, the force applied to climb up the hill will be greater. And there, now we can introduce what work done is. Work done is the force along the path. So that's for our work done. That's the energy required. That's the energy required to travel up a hill or to travel along a path. Force integrated over the space x, which is equal to, let me cross this out so we have more space. So the force integrated along the path is equal to we substitute our force in m du dt dx. So du dt is obviously the a, and f is equal to ma, Newton's second law, times dx, which is the integration over space. Now we're going to use Is it the chain rule? Yes, the chain rule. We're going to use du dx dx dt dx. Now, we know this du dt is equal to this du dx dx dt. It's called the chain rule. I'm sure I've got some material about it. If you don't know about it, you need to learn about it. But if you're not interested in learning about it, just take my word for it. Now, we obviously know that dx dt is equal to u. You obviously know that. It's obvious. You can't pretend you don't know that. So now we have du dx u dx. The x's can cancel, so it now gives us m du. No, sorry. Let's put the u. Yes, mu du. And we know how to integrate. That's a very basic standard thing. So we now integrate that, and it gives us mu squared at time 2. This, my friend, is the change in kinetic energy, because the kinetic energy is mv squared over 2. So m, the mass times the velocity squared over 2. So we've got two different values, so it's the change in kinetic energy, which is equal to our work done. This, my acquaintance, is also equal to, let's look at his notes, it's also equal to what we're going to call, it, so that's the change in kinetic energy, is equal to, is equal to the change in potential energy minus, well, the potential energy is written like that. I'm not sure how visible that is, but yeah, the change in kinetic energy is equal to change in potential energy. Potential energy is our V here, but the potential energy works opposite against the force, so it's always a negative. It's not with respect to the force. So yeah, our force is always working against the potential energy, electric potential, chemical potential, gravitational potential. Any sort of potential force is acting against. So we can define our force f of x as being equal to, dx equal to minus dv. Or f of x. So that's our force along our path x is equal to minus, where v is the potential energy. So we have that v1 minus v2 equal to, where v is the potential energy, is equal to mu squared 2 over 2 minus mu squared 1 over 2. That's the change in potential energy is equal to the change in kinetic energy. We can rearrange so that we have V1 potential energy plus is equal to V2 plus mu squared 2 over 2. Now this is magnificent. This is the total energy of our system at the initial time is always equal to the total energy of our system afterwards. So there, we've just shown the conservation of energy, kinetic energy. So our total energy is kinetic energy plus potential energy, which we've proven is conserved. This is a constant; it doesn't change. So if no force is being applied, if a force is being applied, our energy is constant. The energy in the system is constant. Now we shall go further. So we're interested in when our potential energy is in equilibrium. So we know that the potential energy is. No, it doesn't have to be that actually. So for a standard body in motion is mgh. I'm sure you know that. mgh. M being mass, G being gravity 9.81, and h being the height from the Earth, which we'll probably derive things like that in another video, but for this video we're more interested in waves and harmonics. So, now that we've got that, we shall look at how to derive the waves, which we'll analyze in a way by stating that we're looking for when an object is in stable equilibrium. That is, if you can imagine a ball here, you give it a little push, it will move a bit, but it's in equilibrium, stable equilibrium. Whilst if it falls on something here, if you give it a small push, it will fall off. So this is non-stable. Non-stable. This is stable. Because here the equilibrium is stable, here the equilibrium is unstable. That's very obvious. Don't need to spend long on that. So, when is it stable and when is it unstable? So, bodies like to go to the unstable equilibrium where they have minimum potential energy. So, it is stable when it has minimum potential energy. And you know minimums occur when the rate of change is obviously zero. Value can't change, it can't grow because it's, or you can't decrease at least. It's zero. So this occurs, so all equilibriums occur when dV dx is equal to zero. When dV, so when you have that dV dx is equal to zero and you find your value of x when dV dx is zero, it means it's in equilibrium. If the second derivative is greater than zero, then it means that is your minimum value. And I think your minimum value is when it's in stable equilibrium. If the dV dx squared is less than zero, then this gives you the maximum value for the maximum potential, which means it's unstable. Unstable equilibrium. Unstable, that means your particle is in unstable equilibrium. If you give it a small movement, small perturbation, small anything, it will move quite a lot if it's unstable, which occurs when dV squared dx squared is less than zero. So now we know that the equilibrium is equal to zero. No, the equilibrium is when the derivative is equal to zero. So if we assume the Maclaurin of Taylor series generation. We assume x plus, what do you want? No, we'll just say x. I think this is called Maclaurin. We use the Maclaurin series. Just enough material on that if you don't know what that is. We use the Maclaurin series to express this. Plus, if you're not clear, so we're using the Maclaurin series plus squared. Right, so we're going to assume small values of x and disregard our x cubed terms and greater values. So yes, we've assumed the Maclaurin series for our potential energy and neglecting the x cubed and higher terms, as we're assuming small factors. As we said, equilibrium occurs when the first derivative is equal to 0, so we can cross that out, and then we can say, we cross that out, and then I think v naught is probably also equal to 0. We'll cross that out anyway. Then we have that Vx is equal to the second derivative at x is 0 times x squared over 2. It's pretty nifty. You can write that as kx squared, where k is obviously equal to the second derivative of v prime over 2. Now that's what k is. So we have that a body in oscillatory motion, its potential energy is equal to kx squared. Now this consequence is interesting, and we'll look at it more. So we see kx squared over 2. So this 2 goes away. Now we'll look further. Yes. So now I'm going to rub this all out. So yes, now we've found our function of potential energy. We shall go further. We shall definitely be going further now. And we are going to express, as we originally said, that's, which way shall we do this? F is equal to minus dx, which is equal to minus dx. So this was kx squared. Kx squared over 2. So the derivative of kx squared over 2 is obviously, that gives us minus kx. So there, the force of an oscillatory body is minus kx. K for if it's a spring can be the spring constant, or just some sort of constant related to the system that we're analysing. Yeah, so now we'll go further, stress further. Now that we have that, we also have equal to MA. So we'll write this minus K. Oh, this is where the beauty begins. Mx dot dot obviously means the second derivative of x, which is obviously a. As you know, a is equal to x squared plus id dx squared dt squared. You obviously know that. A is equal to x dot dot dx. Now we have that. Now we write this. Now we have a nice ordinary homogeneous second order differential equation. A nice second order homogeneous linear ordinary differential equation, which I've made a video on how to solve already, and the solution should be something like this. A, B, 3. It will be minus K over M. But for this, we'll be looking at a solution that is of this form here. Right, the form we're looking at. Cosine omega t plus omega t. Right. This is the solution to this. If you plug this in there, you get 0, where omega squared is equal to K over M. And that is the solution to that equation. So now we'll define a few more parameters, such as the other side. So I hope you've got that written down. Put that in your head and understand that. A cosine omega t plus B sine omega t. So then we look further in using H. So we can define the time period, the time it takes for the body to oscillate. T is equal to 2 pi omega. Yes, this is 2 pi omega, which is also equal to 2 pi. You can see how this adds up. I've got the time too. No, we've got some more to do. So yeah, so that's the time period for the oscillations. I've noticed that I haven't even defined what these oscillations are and what simple harmonic motion is. Well, simple harmonic motion is, so you have a pendulum swinging from here to here. Simple harmonic motion is a repetitive motion of a body that goes back and forth in a repetitive manner. So say this is swinging from here to here, and it comes back and just does that literally forever. Just keeps swinging up and down, up and down. That's what simple harmonic motion is. It's a repetitive motion. There's something referred to as the restoring force, which causes, let me redraw that, the restoring force, which as this particle has moved up, the restoring force which is always trying to push it back down to here. So, if we look at this, the particle will swing up here and will have a velocity of 0, and so the minimum kinetic energy of 0, and maximum potential energy. As you remember, our total energy is kinetic energy plus potential energy, which is a constant. So here we'll have a velocity of 0 and its maximum potential energy, and then it will have its greatest acceleration, and its velocity will increase as quickly as possible, and its potential energy, which is in this case gravitational potential, obviously as it comes down, you define potential energy as mh, gh. This, the height at which this finger is h. At each point, the height is h, and obviously as it comes down, the h decreases. So the potential energy decreases, but as energy is conserved, the decreasing potential energy goes to the kinetic energy. So its kinetic energy goes up. These two values are always constant. That's called conservation of energy. So the kinetic energy is increasing, potential energy is decreasing. Here, where the velocity is maximum, this is the equilibrium, as we discussed. This is the center. Has maximum kinetic energy, minimum potential energy, because it doesn't go lower than this in potential energy, as it doesn't literally go lower. But the velocity is high, so it's got the maximum kinetic energy. Then it decreases. Its velocity decreases. It begins decelerating, and as it moves, so this is it moving. Imagine a ball moving. Pendulum moving. It's decreasing its velocity. Because, as I said, it's got a restoring force, so there's a force always trying to push it back to this middle. But it's got inertial force lifting it up by slowly going slower, so it's going slowly. But it stops, comes down with great acceleration, and increases speed. Acceleration keeps slowing down, where it has maximum velocity and then goes back up. And yeah, so that's what the simple harmonic motion is. So now we'll look at damped harmonic motion. So the case we looked at for this was assuming that there is no viscous, no damping. Yes, and let me draw the graph of what it looks like actually. So this is a time graph against say this is a time graph of, let's say, displacement. Let me draw the pendulum. So this is x equals 0 is this line here. This is x is equal to minus a. Is x is equal to a. So a being the amplitude, over time the graph will be go like that. Trigonometric graph, i.e. some sort of sine function, which is the result that we showed here, trigonometric. So that's how the displacement along here varies over time, varies trigonometrically, and its velocity will look like this. What will it look like? Its velocity will look like, yeah, if you differentiate that, you get this. So something like this, I don't know. If you differentiate that, you'll get the, you know, if you differentiate a sine, you get a cosine. Differentiate cosine, you get the sine. And then its acceleration will be the derivative of that again. So that will probably be like that. And so on and so forth. So generally, the example that we looked at was if there was no damping, so it would be like this. The amplitudes at the ends remain the same. Amplitudes there remain the same. Now we're going to look at a damping case. Damping is when there's resistance, so something's slowing it down, like the air particles. And everything, all the values begin to decrease. So it looks something more like this. And it will decrease. As you can see, our function is decreasing over time. This is if it's damped. So if this pendulum was swinging in air, the air particles will be slowing it down, and so then the first time it will go to distance x equals a, x equals minus a, but then after the next swing it might only go up to here, then after the next swing it might go only up to there, and then up to there next time, and then up to there, up to there, until it stops. So that can be depicted here as you see here, it goes to a, minus a, and next time it's a slightly smaller distance. That's because the air particles collides with the air particles which have random velocities and is slowing it down. Well, this frictional force is proportional to the velocity of the particles. So if we take this equation here and you slightly alter it and say that it's what value are we going to use? Let's say alpha. So here alpha is a coefficient which describes the damping, which is as the damping force Fd, I'll call it Fd, the damping force is equal to alpha times velocity. Well, let's not say velocity because we used to already. Alpha times velocity, which is the velocity x dot. So now that we have that, that's what alpha is equal to. That's the damping force. We can now solve this equation and write it neater. In fact, let me rub out everything. It's getting on my nerves. So we have this equation. I think it's this, the damping force plus, that's our differential equation. This is another second order homogeneous equation which is easy to solve. Obviously the answer is, you can look at this yourself, what the answer is. You can apply the quadratic formula to solve this, which would give you, I think it's this, plus minus alpha squared minus 4mk over 2m, which we can go further to do this. We do this, yes, plus or minus. That's what we do, sorry, wait, let me see. Oh, that's what I've done. bigger squared, where this value here is equal to alpha over 2m, and omega is equal to the square root, as we defined before, k over m. So that is the answer to this stamped solution. And that's it for that section of the video. The next videos will go further to look at coupled oscillations, waves of oceans, sound waves, acoustics waves, using various geometry. Thank you for watching. Please stay around for the next video. Have a nice day.